Okay, so good afternoon, everyone. I am Marc Bolaños, and my talk is what is called Deep Neural Networks for Multimodal Learning. And I will talk about some problems, multimodal problems, in which either the input or the outputs are visual and textual. So I will talk about several problems, which let's say are trendy right now. And then I will specifically talk about the ones that our team is working in right now. And here you can see the pictures of the people that we are involved in this. So we are Petia, Radeva, and me from the CBC and the University of Barcelona, and then Casacuberta and Álvaro Peris from the Universidad Politécnica de Valencia, which are initially working in the field of textual translation, and we are in computer for working on this topic. So we'll start reviewing the usual problems which involve this kind of techniques. The first one is image description, in which we've got an image and the model has to generate a textual description of what is happening in that image. Then another example is video description, which is more or less the same, but instead of having a single image, we have a set of consecutive frames which show us some kind of action. Then there's also the multimodal description, which in this case we've got two kinds of input data, the image, and a set of associated descriptions, which are sometimes complementary or sometimes they are different but describe the same image. And we have to generate a different sentence in a different language. Another one of the problems is the multimodal translation, which in this case, the goal is to translate a specific sentence to a different language, and we have an associated image which can give us additional information. Another one is visual question answering, which in this case we've got an image and a question as the input to the system, and it has to generate a valid answer. And the friends in this case detect different regions in the image and generate usually a short sentence for each of them. So problems have some usual components in common. And here, well, you can see that the three, probably the most common ones, which are used in these kind of problems. The first one, you probably know it, are the convolutional neural networks, which are used for processing images, for extracting information from images. Another one is the long short-term memory, which is used for sequences of information and generally used for text, although it could be used also for video, for example, for one frame at each time step. And then another one of the components is the attention mechanism, which is not so widely known, but is pretty useful in this kind of problems. In this case, we've got a set of input vectors, and the attention mechanism uses these vectors and from the previous time step in order to dynamically change a set of weights that will combine the input vectors into a single one. So this has the ability to, given the previous information extracted from the data, adapt it in order to generate the next piece of data. The first problem in which we have been working in our group is the video description one. In this task, we used the Microsoft video description dataset, which is composed of nearly 2,000 short clips from YouTube. And each of these videos has several associated descriptions. So, and in total, there are more or less 80,000 pairs of video and captions. For these problems, we presented, and we recently got accepted a paper in the conference, the International Conference on Artificial Neural Networks, and this is the general model that we proposed in this paper. Here, in this case, you can see that the architecture is divided in two big parts: the encoder and the decoder. And well, this comes from the field of machine translation. Generally, we have an input sentence in our language. We have to encode it to extract information, and then we decode it in order to translate it into a. So with this idea, we wanted to translate the input video into a natural language sentence in this case. And well, in the encoder part, we've got, as you can see, a CNN, which is in charge of extracting information from each of the frames. And each of these feature vectors is used then in a bidirectional LSTM, which is the red part in the architecture. So basically, this LSTM is are two BLSTMs. One of them processes the information in a forward and the other one in a backward one. So it has the ability to, it complements with information that comes from, let's say, from the past to the future, and the other one from the future to the past. And then this information is concatenated for each of the, and then we used a soft attention model. So this attention model, as I said before, is in charge of combining all the feature vectors into a signal, and this output vector will change at each time step, depending on the that it has generated so far. It will change the next vector. And well, at the very end, we've got the last LSTM, which is in charge of generating this sentence. So you can see here that basically the basic formulation of this problem is similar to the machine translation one, in which for generating the next word Y, we take into account all the previously generated words and also the whole video. And here you can see some results that we obtained. In this case, we use these metrics, which are Ble, Meteor, and Fider, which are, well, traditionally were used in these kind of problems, but come from the world of natural language translation. And well, in general, most of them what do is checking if a set of n-grams, so consecutive words, appear both in the predicted sentence and in the ground truth. And it generates just a percentage of how good that evaluation is. And this, well, in this table, you can see the first row, which represents the state of the art in this data set. And they used more or less the same without the objects. So from a CNN trained on object classification. And then when we add, you can improve the measures using an additional set of features which are in charge of describing the scene from the image. And we consider that this could be important because a lot of the sentences describe where the action is taking place. And we can see that, for example, for the CDR measure, but for the rest, it's not so good as the previous proposal. And our intuition was that, in fact, we are here. We will have two set of feature vectors of more than 1,000 components each. So the number of parameters in the model are increased a lot. So we will need a bigger data set in order to train that model. But it has a good potential. And so the final conclusions that we could take here is that using bidirectional mechanisms allows us to extract information from a past to future and future to past fashion. So makes the feature extraction more powerful. Then the attention mechanisms are also very helpful for when we work in a step-by-step sentence generation problem, like in this case. And as a future work, we would like to incorporate also higher temporal level information, like 3D CNN networks, which process the whole video at once. Then another one of the problems that we worked in is the visual question answering problem. In this case, we participated on the CVPR VQA challenge. And well, here we've got a little bit of information of the dataset that we used. This dataset is composed of 200,000 images, and each image has 3 questions, and each of these questions has 10 different answers. And well, one important detail is that these answers are usually very short. So, in fact, most of the groups in the challenge used in their model, instead of generating word by word, they used just a softmax, which classified, which outputted the whole answer of the sentence at once. And this is the proposal, our proposal for the challenge. In this case, you can see that the main difference is that we've got not only images as input, but we have also a sentence, which is a question, associated to the image. For describing the image, we used a technique called kernelized CNN, which basically extracts object proposals from the image. And these both object proposals are combined into a single vector using, well, learning a Gaussian mixture model and applying a Fisher vector representation. And then we also used visual embedding while learning the model, adapting this representation. For the question part, we used a text embedding, which, well, we saw that this improved and, well, we adapted this representation during training also. And additionally, we used bidirectional LSTM for representing this question. And finally, for adapting both modalities, we just applied the element-wise summation on the components and applied the softmax. In this case, for generating the answer, as I said before, we take into account the whole question and the image, so we don't generate it step by step. Here you can see some results of our model. So, for example, our model is able to, in the first example, it's able to count, well, it's not easy to see here, but here there is another head of another zebra. So it's able to find and count. Then it's also able to detect actions here. The dog is playing frisbee. Well, classify animals, answering yes or no questions. Well, it's quite robust, and it's able to work on different kind of answers on questions. And here, there is a small summary of the results that we obtained. The most important parts here is that if we compare it either using LSTM or not using it in the first and second rows, well, first of all, I must say that the measure that we used here was the accuracy, but one specific accuracy computed for this challenge, and it provided also information about separating just the questions whose answers are yes or no, the ones that are a number, and the rest of the questions, and then the overall is the average of all of them. And well, as I was saying, if we apply a bidirectional LSTM on the question instead of a simple LSTM, the improvement is not so big in this case, but it helps us a little bit. We also saw that when applying the model on the test set, it helped very much if we used both the training and the development sets for training. And this is because, well, the data set is not big. It's not very big for more data for improving the result. So to sum up, we could say that for data sets like this, which have short answers, classification models work better than generative. Then also using methods like kernelized CNN information that describe different parts of the image is also pretty useful. And then also using pre-trained but adaptable representations, both on the image and on the question, is pretty useful. Then, just as a brief summary, we also have worked in image description, but in this case we don't have any publication. So, well, in this case you can see that it's a much simple model, but well, we plan on working on this also in the future. And we also worked on multimodal translation, which in this case, as in the question answering, we have, and in this case we had to generate the output sentence instead of just classifying it. Well, as feature directions, we are planning on incorporating several state-of-the-art architectures to our models. For example, we want to try using high-volume networks and compact linear pooling models, which have been used for some highly performing groups. And also we want to use class activation maps for interpreting the information extracted by the CNN, and also as an additional attention mechanism for what have to focus in the image. And to finish, well, this was more because of the talk I gave the last day, but well, we wanted to listen because of this network, because thanks to it we were able to work together with the UPV and start this collaboration. That for now it has been very useful. And well, if you're interested in this kind of problems and want to try some easy code, you can test our VDCnet model, and that's all. Thank you. Any question?
So I guess the first thing is not a question, just information that I'll be aware that you mentioned in the description that you were considering using 3D convolutions. Are you aware that Western Alberto Montes already imported them to Keras? C3D model? Yeah, no. So maybe that's useful, I guess, for you. I can give you the link.
Okay, yeah. And let's train some model. Yes.
He didn't train it. So the model was published in Spain. I know that he did something for the Keras and it was highlighted by Keras special library. Supposed to be. So it should make things a bit easier for you, I guess. Then, can you put that? So the before question answering is key. So you do this twice, mention?
Yeah.
And that same start. So exactly. So how do you manage that?
Yeah. Well, we control this just like so with the visual embedding that converts the KCNN, the length of the KCNN to any length that we decide, and then the bidirectional and the bidirectional line to different features. One from the forward and the other one from the backward. So we just have to make sure that concatenating them have the same length than in the visual.
So that's not just a for connected. When you have proper visual
yeah,
that doesn't connect.
Yeah. So we are just learning
Okay, then the next question is between visual question answering and the translation one. So in both cases, you have a question and a sentence, and you cannot relate it to answers there. There is no image to kind of answers. What's the gain of having
in this case?
I would say both. This was an interpretation.
Yeah. Well, in this case, it just generates the most probable answer, let's say, associated to that question. For example, if it's asking about some color, then if the most of the answers, the color is red, it will be red. Be related to the image. And in the, well, in this case, because as I was saying in the introduction, here the image is just some additional information. So what we really want is to translate exactly that. So in this case, even if we don't use the image, the result is pretty good. It just gives some little information.
So I guess, if you measure, then that would be interesting to measure, like what's the gain that you get having this?
Yeah, well, I don't have the numbers here, but in this case, it's not very much. It's very much. And the other one, well, it's better, but obviously the data set. But it's important to see what is, because if we, for example, if you ask about what animal can you see in the image, we would just say something random. Probably a random, but in this case it's a graph. Yeah. In this case we didn't measure it, but probably it's good.
One final question. Very curious. If you want to mention that you were thinking about using the classification maps, additional attention mechanism. Have any idea about how to do it? Because you need to know the plans, right?
Yeah. Well, in fact, we are planning to use that question, the vocabulary, well, in order to find that specific information in there.
You are going to try to find each of those words. You just do maybe just a hard matching, like word by word from the question to see if there's one of the classes that you will train.
Well, or we can train also, I mean, which instead of putting the objects of the method, we use the vocabulary of the person. For example, so we can say the word which finds the animal or finds the girl, and it gives you the reason.
I think that they're going to find class will correspond to a word, a possible question, and so for that image, positive for the classes where is that. So
yeah, in case that you want to use all the words, yeah, but maybe the word is not very informative.
yeah, so it's quite. Research that will somehow use of these. I guess that also there's something in the KCNN right
Yeah. Yeah, probably. But
that was trained with me.
But the KCNN, yeah, but the KCNN is pre-computed. And you cannot in training Python. But if you train the classification maps, you can validate it. So in fact, we have applied some tests for this. So using this, the vocabulary of the question. Well, we have only used this on the question yet, but the maps seem to be pretty good.
Which are very important. Thank you very much.
Oh. Here we've got Mariela and Stefania. I don't know if they want to ask something.
Yeah, for me, can you hear me? Yeah. For me, can you hear me?
Yeah.
Hello. So for me, yeah, can you state please in clear way the advantage of having the bidirectional LSTM instead of the simple one?
Well,
just justify this conceptual level.
Depends on the. Sorry.
If you can just justify this conceptual level, yeah.
I didn't understand that.
If you can justify the use of a bidirectional LSTM.
Yeah. Yeah. So as I was saying, it depends on the problem. Cases the question answer very good. Well, it improved so many points. But in this other case, in the video description, we saw that when we get information from the video to the past, the network is able to get or action informations that are not so easy in the forward. An important part is that, for example, in this case, if we just used a simple LSTM, we would remove this part of the model. So this means that for the first frame in the video, we would just take into account the information of this frame, and we would just output this information. But for the last one, we are taking into account all the frames. It's just the LSTM is like combining the information from all the frames in the video. But in the first one, if we have the opposite network also, we can see that in the first frame, it will combine all the frames in the video. So it's able to grasp information from more data than. So I don't know if I've explained it very well. But.
So you are capturing future and past information at the same time, right?
Yeah. So in the simple one, in the first time step, we only have information from the first image.
Yeah.
But in the backward LSTM, we already have information from all the frames. So it's really a combination of both.
Okay, but in general, why people they use a do you know other example, for instance, where a bidirectional LSTM is useful?
Well, here.
I don't. Sorry. So, for instance, for which kind of problem has been used for the first time?
Has been used for the first time.
Yeah, if you know that. I'm just asking.
I've seen it in the first time. I don't know the first time.
You don't know? Okay. Okay, don't worry. Okay, thank you.
I don't have any question, Mark.
You don't have any question?
No.
Okay. Well, yeah, it was pretty complex, but one of the structures that they used is this one, the compact linear pooling. And well, here they applied a convolution, but a different kind of convolution using Fourier transforms. Which, well, instead of using, for example, here, for combining the both modalities, we used a simple summation, but instead of this, we used the compact. Well, we use also a tension model. But I think that these structures were the the most important ones. But
Marc?
Which component with which component. And then you do this also which part of the which part. This is then this is a relationship. Well, you comes from years ago, some other people that are interested in people. She knows where to get what to get. It's really practice. So I explain
Remind me, so something called second order theory, like some little features that was focused on the obviously the school doesn't have. But I was going to learn now if we provide this world based on this feature for take a look at again.
Okay, so thank you.
hasta luego.
Leo.